Okay, let's jump right in.
Yeah.
For anyone who follows what we do here, we spend a lot of our time analyzing these huge, almost invisible systems.
Right, the strategic infrastructure.
Exactly. The energy grids, the water networks, all the logistics that make modern life even possible. But today, we're making a bit of a pivot.
A significant one.
We're moving from that raw infrastructure to something, I think, more foundational, the civic structures.
Yeah.
We're talking about the actual places where human potential, where health and knowledge are. Well, where they're manufactured.
And that's the perfect word for it. We're shifting from pure engineering to architecture, but it's architecture seen through this very specific lens of statecraft.
Statecraft, I like that.
Yeah, because our entire deep dive today comes straight from a single high-level strategic document. It's the KING-KAMBUF National Building Design Command Brief, and it's dated Sunday, December 7th, 2025.
And what this brief does, it basically defines the design rules for these civic structures that are, well, they're mission critical for a nation's stability. And I think this is the key word, it's sovereignty.
Absolutely. And the focus for this whole planning cycle is captured in the theme of the day. And honestly, it's one of the most direct and exciting mandates I think we've ever come across.
It's called Heal, Toner, Learn Megacampuses.
Yeah.
Just the name itself. It feels like it defines a whole generation of what needs to be built.
It really does. The brief defines the structure as an integrated health plus education city anchor. And it's designed very specifically for these rapidly developing KING-KAMBUF city-states and their diaspora hubs. The mission is, well, it's completely unambiguous.
Which is?
To build resilience by combining all the elements that are necessary for, for human flourishing.
Okay, so let's unpack that phrase, integrated health plus education. For you listening, what are we really talking about on the ground? It sounds massive, like merging a major hospital and a huge university into one system.
It is massive. And the goal is layered, but at the end of the day, it's all about one thing: independence.
Independence, okay.
So layer one is what the brief calls health sovereignty. That's the capacity to actually care for your own population, to do your own advanced medical research, and to respond to a pandemic without being dependent on anyone else.
And layer two?
Layer two is knowledge production and workforce formation. By merging these huge health facilities with vocational schools, with technical institutes, you create this self-feeding loop of skill development.
So the people who maintain the hospital are trained right next door to the hospital.
Exactly. You train the nurses, the doctors, but also the technicians who keep the lights on and the oxygen flowing. It's a closed loop.
So these places aren't just buildings. They have an actual operational role baked right into their design.
Precisely. The brief says they have to fulfill 3 operational roles at once. First, they have to anchor their neighborhoods, provide stable jobs and services.
Okay.
Second, they have to actively regenerate the districts around them, drive economic growth, set a new standard for quality. And third, they have to operate as these big regional systems, linking up with other health and education hubs.
The list of components required in the brief, I mean, it's just staggering. It's a whole city in one site.
It's a total systems requirement. You're combining primary and tertiary healthcare. So everything from a community clinic to an advanced surgical center. You've got research labs, vocational institutes, teacher training, digital learning hubs.
And housing. You can't forget the housing.
Crucial. Staff and student housing is non-negotiable for attracting talent. Then you have public spaces and all the logistics to support it, power, waste, deliveries. The level of coordination is just immense.
And the thing that makes this such a unique challenge, and this is spelled out in the brief, is the contextual mandate. These designs have to be for African and diaspora context.
Which means they have to respect real-world constraints.
Right. Real procurement schedules, real construction challenges.
The document is so clear on this. These cannot be, theoretical blueprints that assume perfect supply chains or unlimited money. They have to be buildable, scalable, and affordable right where they're needed.
And that's why this deep dive is so critical, isn't it?
Yeah.
Because it's not just about big ideas. It's part of a much larger systemic effort we've seen before with things like the coastal rings or the water energy networks.
Exactly. It's the next logical step. Okay, so let's dig into the tactical difficulty.
So the vision is huge, nation building by design. But the brief, it just immediately cuts through all that high-level strategy and gets right to the point. It gives us the rotating master challenge focus, advanced.
And this is where we hit the ground truth of what architecture actually is.
Which is?
Construction means and detailing. For the design teams working on this, this is the real intellectual hurdle. The brief basically says that the biggest barrier to turning the civic ambition into, buildable reality It's not the money. It's not the vision.
It's the execution.
It's the execution. It's the wall section. It's the roof joint, the pipe connection, the small stuff that makes everything else work.
But why is detailing considered the advanced challenge? I think for a lot of people listening, advanced sounds like, I don't know, a hospital robot system or something.
Yeah.
But the brief says it's the mundane parts.
Because sophistication without robustness is completely useless.
Yeah.
I mean, you can have the most perfect program, the most beautiful design, but if the facade leaks after 3 rainy seasons...
Or the AC needs some special part from Germany.
Exactly. Or if the roof joint fails, then the entire mission, health sovereignty, knowledge production, it's all compromised. The real pivot point here is durability and ease of repair. The charge is to design this high-performance system that can actually be built and maintained by local people under really challenging conditions.
That is such a fundamental challenge that designers in, say, the global north just rarely have to face. They just assume a reliable supply chain is a given.
Right. So for this project, there are these mandatory construction strategies. They are the 5 non-negotiables that will determine if these projects succeed or fail.
Okay, let's break them down. What's number 1?
First is modular systems and phased delivery. This is just essential for managing money and for rapid deployment. A city-state can't just put everything on hold for a 5-year construction project.
So you get usable parts of the campus online sooner.
Precisely. It has to be delivered in these usable, certified chunks. You know, phase 1 is the emergency clinic and the vocational center. Phase 2 is the teaching hospital wing. Phase 3, the research labs. Modularity lets the whole system grow with demand and with funding.
So instead of a static blueprint, they're really designing a kind of dynamic, expandable kit of parts. What's the second requirement?
Second, and this is maybe the most crucial for the long term, is climate-appropriate envelopes.
The building skin?
The skin. This is all about the operational budget down the line.
Right.
We're talking about designing facades that manage extreme solar gain, high humidity, torrential rain, and do it in a way that reduces the reliance on expensive mechanical cooling and electricity.
So deep overhangs, perforated screens, things like that.
All of that. Materials with high thermal mass that regulate temperature naturally, because if the building is constantly fighting the climate, the maintenance budget is going to lose every single time.
Which I guess leads us directly into the post-pandemic reality of designing any healthcare space now.
Absolutely. The third non-negotiable is infection control details. This is a lesson learned the hard way from recent history. It just fundamentally changes everything. How you design flow, manage air quality, select your materials.
So dedicated pathways for contaminated materials, for example.
Yes, and making sure all the high-touch surfaces are non-porous and easy to clean. And critically, building in the capacity to immediately convert standard wards into isolation units if you need to. This kind of detailing is literally about defending life.
And what about speed and quality? How does the brief address that?
Number 4. Prefabrication strategies. This is all about speed and quality assurance. By manufacturing key components, structural columns, facade panels, or, and this is critical, the entire MEP spine.
MEP being mechanical, electrical, and plumbing.
Right, the guts. By building that in a controlled factory environment, you get higher quality and much quicker assembly on site. You avoid the quality issues that can sometimes plague these huge projects.
And finally, the one that determines if this massive investment lasts for 5 years or for 50 years.
Maintenance-ready construction. This is the strategy that directly confronts that constant problem of life cycle neglect. If the system relies on specialized foreign parts or systems that are all sealed up and hidden behind walls, it will fail.
It has to be repairable.
It has to be robust, easy to access, use standard parts you can get anywhere. The design has to anticipate, not resist, the need for ongoing repair and adaptation.
That sets an incredibly high bar. You're asking designers to think like construction managers and facilities operators, not just architects. So how does the brief actually enforce this? What do the teams have to deliver?
The work is split into 2 really stringent blocks. Block A is the concept. This requires the big picture stuff. The program diagram, so showing how all the functions relate. The flow separation logic, which is proving how you keep patients, students, and services from crashing into each other. And the climate and construction logic. Basically, the argument for why your design approach is actually buildable and appropriate for that specific place.
And then block B, this is where the theory hits the pavement.
This is the deep dive into the specifics. Block B is details. It demands tangible proof that this thing can be built. First, a buildable section at a proper scale showing the clear relationship between structure, the envelope, and those MEP services. It's not a pretty picture, it's a technical map of how the building actually works.
And a specific detail.
A specific envelope or MEP detail. They have to focus on one critical junction. Maybe it's where the roof meets the wall, or a plumbing riser detail.
Okay, let's pause on that. For anyone listening, why is detailing the junction between, say, an electrical conduit and a water pipe so critical? It just sounds so tedious.
Yeah, because that's where failure starts. In good, robust construction, all those MEP systems, the hitting guts, they're managed in these clear, accessible corridors or spines. If you have to rip out a wall every time a valve needs to be replaced, the building is just a nightmare to operate, and it falls into disrepair really quickly.
I see.
That little detail proves the whole system is designed for access, for durability, and for redundancy. It's the difference between a building that lasts a decade and one that lasts a century.
And finally, they have to quantify the impact. Annotated ESG metrics.
Right. The design has to prove its worth beyond just looking good. The ESG metrics demand numbers. Beds per 1,000 people, students graduating per year in critical fields, energy intensity, how many kilowatts per square meter, and a resilience rating. How well does it withstand a disaster?
So it connects the architectural drawing directly back to the national mission.
Exactly. The architects are functionally required to prove their positive social and governance impact before a single shovel ever hits the ground.
All right, this is where we really see the principles get tested. The brief lays out 10 distinct real-world scenarios. It calls them portfolio trills. And it's just this stunning survey of challenges across the continent and the diaspora.
They're strategic pressure tests. Each one forces the design teams to test their construction logic against these very specific, very real regional constraints.
So it proves that the Heal to Learn megacampus isn't some monolithic template.
No, it's a flexible, adaptable system that has to respond to these wild variations in context. From a dense megacity to a remote rural area, from a flood zone to a hurricane path.
Okay, let's start with the extreme challenge. The megacity. Scheme 1. Nigeria, Lagos Mainland, Heal to Learn District.
Lagos Mainland is the ultimate constraint. It's just no land. So you have a teaching hospital, a nursing school, and a technical college all squeezed into this dense transit corridor. The core challenge is simple to say, build vertically, but an operational nightmare to actually do.
And that nightmare is?
Strictly separating clean and dirty flows in a multi-story, high-traffic building.
So let's get granular on that. How do you stack a hospital on top of a college and make sure, say, a nurse with sterile supplies never crosses paths with the waste collection, or a vocational student carrying tools?
The architecture has to act like a multi-layered filter. And the deliverables for this scheme highlight that. They ask for hospital education stacking sections. This means you need dedicated vertical cores.
So separate elevators?
Separate elevator banks, separate stairwells, separate service shafts for patients, staff, and logistics. The hospital has to be on the most sterile, controlled levels, usually higher up for better air quality, with the educational spaces acting as a buffer on the lower, more public floors.
And the required detail is really telling. An infection control facade with shading and operable ventilation. That seems to blend all the requirements together.
That facade is working overtime. The shading deep fins, perforated screens, that manages the intense Lagos sun to cut down on cooling costs. The infection control part dictates the materials, so they have to be easy to clean, non-porous. And then the ventilation strategy.
Operable windows.
Crucial, not just for fresh air, but as a low-tech, zero-energy backup in case the mechanical ventilation system fails. The design has to work even when the high-tech stuff goes down.
And the precedents here provide a pretty sobering reality check. There's success in scalable expansions, but the caution notes overcrowding and chronic maintenance failure in some existing Lagos public hospitals.
The lesson there is that verticality magnifies failure. If you have a structural or an MEP breakdown on the 8th floor of a building like this, it can paralyze the entire operation. So the design has to include redundant infrastructure, twin power feeds, decentralized water storage, clear maintenance access to stop that kind of systemic collapse.
Otherwise, the facility becomes a liability.
Exactly, not an asset.
Okay, moving to another project of immense scale. Scheme 7. Ethiopia University Hospital for a 10 million person metro in Addis Ababa. So if Lagos is about density, Addis is about sheer volume.
It's all about extreme scale and logistics management for tertiary care that serves millions of people. I mean, just imagine the daily movement of food, linens, pharmaceuticals, medical gas, waste. Not to mention staff, students, and emergency cases.
The volume is mind-boggling, which is why the focus is on a service tunnel section and this meticulous detail on separating patients, staff, and materials. So why are service tunnels an architectural must-have at this scale?
Because the efficiency of the hospital is determined by what happens out of sight. Service tunnels, or at least dedicated utility corridors, they ensure that all the necessary clutter of operations, the loading docks, the waste compactors, the maintenance crews, is completely separate from the patient and academic experience.
Hmm.
If every delivery truck and waste vehicle is using the same roads or elevators as the patients, you get bottlenecks, sanitation risks, security problems. Service tunnels guarantee that operational flow 247 is just unimpeded.
The success here points to the Tikur expansion concepts, so they understand large-scale medical education. But the caution is about congestion from poor service planning.
And that's the danger of only focusing on the shiny facade.
Hmm.
You can build a beautiful 500-bed tower, but if the basement infrastructure, the generators, the chilled water plant, the loading bay, if that's poorly planned, the whole system just grinds to a halt.
So you have to spend as much time and money on the guts of the building.
As much, if not more, than you do on the public face.
All right, let's pivot to schemes that are defined more by their relationship with the natural environment. First up, Scheme 3, Kenya Kisumu Lakefront Medical plus Environmental Institute.
This is a really sophisticated project. It links healthcare directly to environmental science, and it's right there on the shore of Lake Victoria. So the challenge is twofold. You have to design for flood resilience because the lake level changes seasonally.
Right.
But you also have to manage the highly sensitive research needs for waterborne diseases and other public health threats that are common in that region. The campus is basically exposed to the very thing it's studying.
So the design has to embrace the environment, not fight it. The brief requires a site hydrology plan, a raised building section, and this detail of a floodable ground floor with durable finishes. How does a floodable floor actually work in a high-tech campus?
It's a design of strategic surrender. Instead of building these massive, expensive dikes, you just lift all the critical functions, the clinics, the labs, the classrooms, up above the known flood level.
Okay, so the ground floor becomes what?
A sacrificial transitional space. It might be parking, open-air lobbies, low-value storage. And the finishes, concrete, durable ceramics, modular, accessible services, they're all chosen because they can be completely underwater, easily hosed down, and put back into service as soon as the water recedes.
The successful precedent is the Aga Khan Hospital in Kisumu, so it's viable. But the caution is that a lot of the surrounding developments have failed to address this seasonal flooding. So the goal is to set a new standard.
Exactly. The new campus has to be a resilient anchor if there's a major flood. It has to provide continued emergency services when everything else around it is failing. And that means paying meticulous attention to service entrances, making sure they're accessible via elevated ramps even when the area around them is submerged.
Okay, so from water to wind, another extreme climate scenario. Scheme 8, Caribbean Jamaica, a climate-resilient health plus learning hub.
Here, we're talking about genuine disaster readiness, a hurricane-resistant coastal campus. The core challenge is ensuring absolute continuity of care post-disaster. A hospital is unique in that way. It's not enough for it to just survive the storm.
It has to be running at peak capacity the moment the storm passes.
That's when the region needs it most.
The deliverables reflect this. An elevated site plan to protect from storm surge, a robust structural section, and the detail of a storm-rated roof plus shutters. That structural section must be a technical marvel.
It has to be over-engineered. We're looking at redundancy in the structural frame, probably a moment frame system that can resist Category 5 winds. You're not just anchoring the roof against uplift. You're making sure critical equipment like HVAC units and oxygen tanks are secured against flying debris.
But the caution here is maybe the most critical point. Power loss, crippling hospitals after storms. What's the architectural solution to that?
The architecture has to integrate total energy autonomy. And this isn't just a generator in a shed. It's a hardened, decentralized system.
So solar.
Solar arrays that are secured against high winds, battery storage systems, and hardened fuel storage, often buried. The building itself, the structure, has to be designed to contain and protect these energy systems so that when the grid goes down, all the essential life support, the ventilation, the surgical lights, the IT, the oxygen production, it all stays fully operational for at least 72 hours.
So that detail, the energy autonomy, that's what defends life.
That is the detail that defends life.
All right, these next few schemes seem to focus less on climate challenges and more on using the campus as a tool for social and economic development. Starting with Scheme 2, Ghana Accra Community Health plus Teacher Training Campus.
This one is an exercise in resourcefulness, and dignity. It's a rayon-scale campus, so a neighborhood anchor right next to informal settlements. The core challenge here is delivering a sense of permanence and quality while sticking to very low-cost, climate-responsive construction methods.
It's about delivering dignity, but
Yep.
without importing unsustainable luxury.
Exactly. The deliverables call for a cluster plan with courtyards to maximize passive cooling and security, a hybrid block section for clinics and classrooms, and this crucial detail, using earth blocks plus a ventilated roof.
Talk about the earth blocks. Why are they a strategic choice here?
Well, earth blocks usually stabilize compressed earth blocks. They are the ideal anti-dependency material. They're sourced locally, which dramatically cuts the embodied carbon of the construction. And crucially, they have high thermal mass and excellent breathability. Meaning, the building naturally regulates temperature and humidity far better than a standard concrete block wall. So you minimize the need for expensive air conditioning. Then the ventilated roof, which is often a double roof system, lets the trapped heat escape. You're maximizing comfort with passive, zero-cost energy strategies.
The success story here is Ashesi University's campus, which shows this is possible. But the caution is a big one. Imported systems failing because of spare parts dependency in West Africa.
That is the operational Achilles heel. I mean, if the campus relies on some proprietary air handler or an imported pump that takes 6 months to get a replacement part for, the whole system becomes non-functional. The design has to favor components that can be made, maintained, and replaced locally. It's not just architecture, it's economic policy in a wall section.
Okay, next up, Scheme 5. South Africa, a post-apartheid health plus TVET anchor in the Eastern Cape. This is a rural setting, focused on building an economic foundation.
Yes, the context here is a rural health and trades campus. It's dedicated to building a sustainable skills pipeline. So the core challenge is making the hospital itself the primary classroom. You're training the nurses, yes, but you're also training the certified electricians, the welders, the HVAC techs, who will not only maintain this facility, but service the entire region.
And the deliverables reflect that dual function: a linear campus master plan for growth, a workshop clinic section where the two functions meet, and the detail of a robust truss plus service corridors. Why the robust truss?
The robust truss is all about utility and flexibility. Workshop spaces need these simple, open-span, high-ceiling areas that you can easily reconfigure as training needs change. The industrial aesthetic means it's durable and adaptable. And the service corridors are vital again, but here they're also teaching aids.
How so?
That's where the apprentices learn the anatomy of a building. They practice maintenance and repair on the live infrastructure of the campus.
UN Habitat case studies show this model can work. But the caution is a common one: isolated campuses without transit access.
Right. If the campus is physically isolated, that skills pipeline stays empty. So the architectural design has to include integration with new transit links bus stops, dedicated roads, maybe even staff housing designed around easy access. You have to design the access as rigorously as you design the operating room. Otherwise, it's just an impressive, expensive monument that serves no one.
And the final community scheme, Scheme 9. The African American context, a Southern U.S. heal-to-learn justice campus. The challenge here is very different. It's about social remediation.
It's about addressing decades of systemic neglect. The context is historic underinvestment in health equity and trades training within an existing urban fabric. So the challenge is to correct that history with physical investment that is sensitive and sustainable. And that often means less new construction and more strategic intervention.
Which is reflected in the deliverables: a campus infill plan, adaptive reuse section, and the detail of a retrofit envelope upgrade.
Adaptive reuse is so key here. You respect the existing community, you minimize demolition, and the retrofit envelope upgrade new windows, modern insulation, better air barriers. That's the most immediate way to translate an architectural project into community benefit. It dramatically lowers utility costs, which frees up money for medical services, and it improves the indoor environment for everyone.
But the caution here is ethical and systemic: the risk of gentrification without specific displacement safeguards. Okay, let's address this head on. The campus is designed to anchor the neighborhood, bringing in investment and jobs. But we know that investment often drives up property values and displaces the very community the campus is meant to serve. How can architecture actually incorporate safeguards against that?
That is the critical question. A design can't just rely on policy to solve that. It has to embody the safeguard. So that means integrating things like community land trust agreements or mandating low-income housing components directly into the campus plan.
So for example,
For example, if the campus includes staff and student housing, A significant portion of that has to be permanently deed-restricted affordable housing. The architecture itself, the permanence of the public spaces the community uses, it has to signal a long-term commitment to equity, not just market opportunity. The design has to encourage stability over speculation.
All right, let's turn to the final block of schemes. These seem to prioritize modern systems, technology, and advanced construction. First, Scheme 4. Senegal, a Dakar Digital Health plus Nursing Megacampus.
This is the high-tech face of health sovereignty. The context is telemedicine, advanced data labs, and nurse training. The core challenge here is fusing the digital world data security, networking seamlessly with the physical reality of patient care. The brain of the hospital is now digital, and that brain needs physical protection.
How does the building protect the data? The deliverables mention a data clinic adjacency section. There's a really interesting detail. Secure server cooling using passive chimneys. Can you break that down? A passive chimney for a server room sounds like a low-tech solution for a high-tech problem.
It's the perfect marriage of necessity and ingenuity. I mean, high-density server equipment generates a massive amount of heat, right? And that's usually managed by these energy-guzzling AC units. A passive chimney is a structural air management system. It's a vertical shaft that uses natural convection.
Hot air rises.
Hot air rises. The chimney captures that server heat and just draws it up and out of the building. It slashes energy consumption, reduces the mechanical load, and it provides a crucial non-electronic backup cooling system if the power goes out. It protects the data center while maximizing efficiency.
And the success is noted in Dakar's medical digitization pilots, so we know e-health is viable. The caution, though, is an acute one. Underpowered infrastructure crippling these e-health rollouts.
The failure point is always the physical infrastructure. You can have the best telemedicine network in the world, but if the campus can't maintain robust, redundant, stable power, the data labs fail, the system crashes. So the architectural solution has to prioritize energy resilience, especially where the local grid is inconsistent.
Next, Scheme 6. Rwanda, a modular district hospital plus medical school. Rwanda is often held up as a model for rapid quality infrastructure.
And this scheme is all about optimization. The core challenge is balancing speed, guaranteed sterility, and long-term permanence using fast-deploy modular systems. The question is, can modular construction, which is often seen as temporary, can it achieve the lifespan and robustness you need for a sovereign medical facility?
The deliverables show how. A modular grid system, an expansion axonometric showing how you add new wings, and the detail of a prefabricated MEP spine. Why is prefabricating that entire MEP spine so strategic in a modular context?
Because in a hospital, something like 70% of the cost and complexity is in those hidden services. Prefabricating the MEP spine gives you quality control, consistency, and speed. It arrives on-site as a single coordinated tested unit ready to plug into the structure.
And that's critical for sterility.
Critical. It ensures that complex systems like medical gas delivery and specialized ventilation meet these rigorous standards no matter what the local site conditions are like.
And yet, that familiar caution pops up again. Imported prefab without local maintenance capacity. If the modular parts are too foreign, the speed advantage becomes a long-term liability.
The modularity has to extend to the maintenance protocol. The systems have to use standard international connectors. The manufacturer has to supply detailed, locally adaptable manuals. A key design solution is to specify components that have multiple non-proprietary suppliers, so you're not held hostage by a single, distant parts manufacturer. The system has to be designed for local disassembly, repair, and reassembly.
And finally, we arrive at Scheme 10. The KMBUF prototype city-state, the Continental Health Knowledge Capital. This is the flagship, the statement piece.
This is the ultimate test of the whole mandate. It's the flagship sovereign campus. And the core challenge is the most subtle one. Balancing that symbolic identity, that sense of monumental pride and national destiny with ironclad, day-to-day operational efficiency. It has to look like a capital, but function like a seamless world-class machine.
And the required outputs include a monumental hall section and this phrase, ceremonial yet modular construction. That just captures the entire conflict between pride and pragmatism.
It encapsulates the whole philosophy of nation building by design. The solution is often a hybrid approach. The public-facing, ceremonial parts, the entry hall, the library, they might use permanent, locally sourced monumental materials to establish that identity and grandeur. But behind that facade, the critical operational parts, the operating rooms, the clean wards, the lecture halls, they must be built using the highly efficient, reproducible, standardized modular systems that were developed in the other 9 schemes.
The success stories are integrated campus capitals all over the world. But the caution is a big one. The risk of monumentality without service coverage.
And that is the gravest threat to a flagship project like this. If all the resources get spent on the grand lobby or the symbolic tower, and there's not enough budget left for the high-spec mechanical systems, for the redundancy, for the maintenance budget, then the entire project fails its sovereign mission.
The function has to drive the form.
Rigorously. You can never sacrifice the necessary utility for unnecessary spectacle, because the ultimate symbol of sovereignty is a system that works reliably for its people.
So we've gone from this macro vision all the way down to the micro detail of these 10 schemes. Now let's just zoom out for a minute and place this whole thing in the broader strategic context where it belongs. This is not just a collection of building projects.
No, it's policy delivered in concrete and steel. That framing is essential. The brief explicitly positions these designs within the AU Agenda 2063, that's the African Union's long-term transformation plan, and major African Development Bank health infrastructure reviews.
And why is that? Why that specific link?
Because those analyses all identify the co-location of health and education as a top multiplier for human capital.
A multiplier, not just an addition. What does that exponential growth actually look like on the ground?
It creates the symbiotic environment where the output of the whole is just so much greater than the sum of its parts. I mean, when you train vocational students to install the solar panels and maintain the sterile ventilation systems of the teaching hospital next door.
Their education is immediately certified.
And context-specific, and applicable to the region's needs. When you train medical students in a facility that has the latest digital health labs, the quality of care just improves exponentially. It accelerates the rate at which you can form and, crucially, retain human capital locally. It directly counteracts brain drain.
The brief also makes it clear how global crises have just fundamentally rewritten the rules for design. It talks about post-pandemic design shifts. The assumptions of architecture from before 2020 are basically obsolete now.
Completely obsolete. Every design now has to have 3 non-negotiable features embedded in it. First, that heightened emphasis on infection control design we talked about. Air change rates, isolation rooms, clear flow separation. Second, the necessity of oxygen autonomy.
Which is a huge infrastructural requirement.
Massive. No sovereign health system can rely on external global supply chains for oxygen. The campus has to have the physical infrastructure to generate, store, and distribute its own medical-grade oxygen.
And third,
An intense focus on local medical training capacity. The facility must be architecturally designed to maximize the number of students, teachers, and researchers it can host, so that in the next crisis, the nation can staff and supply its own facilities instead of relying on international aid workers who might not be able to travel.
all of this just reinforces the fundamental philosophy of the brief, what it calls the urban systems approach.
Campuses are no longer buildings, they are urban systems. It's a total shift in thinking. When you design that Kisumu facility, you're not just designing a clinic, you're designing a strategic asset that manages disease research, water security, and flood resilience for the entire city region. The architecture is explicitly mandated to function as essential city infrastructure. It links everything together.
And to make sure that this systemic thinking and accountability runs through the entire process, the brief mandates these extraordinarily rigorous working methods.
The operational discipline is as important as the design. They require this very specific structured archiving system. KMBF Studio 2025-1207 Heal to Learn Megacampuses. That's not just bureaucratic clutter.
It's about knowledge sovereignty.
Exactly. It guarantees traceability, accountability, and the ability to transfer knowledge effectively between all these projects.
And the required portfolio tags make sure every design is evaluated on its strategic contribution, not just how it looks.
They have to tag every project with its theme, its focus, which is construction means and detailing its scale, the quantifiable ESG metrics, and most importantly, the lesson learned. They are embedding the feedback loop directly into the archive. So the design process becomes this collective, continuous knowledge production machine where failure isn't hidden. It's analyzed and cataloged to prevent it from ever happening again.
You know, this whole deep dive has really shown the breathtaking ambition of this Heal to Learn mega campus mandate. We've gone from this high-level vision of health sovereignty all the way down to the specific engineering of a storm-rated roof in Jamaica or using earth blocks in Ghana.
I think the key insight for you listening is this incredible strategic balancing act that's required. This design brief is a detailed strategy for sovereign development. It demands this synthesis of high-technology data security, telemedicine, modular systems with robust, low-technology passive cooling, simple trusses, locally sourced materials.
And all of it has to be executed under the relentless pressure of real-world constraints.
It's the highest form of purposeful architecture. It's intrinsically tied to the public welfare and the future capabilities of millions of people. And the final directive from King-KAMBUF in the brief, it just encapsulates this entire monumental mission perfectly.
It elevates the whole task, doesn't it?
It reinforces the absolute connection between the health of the body, the education of the mind, and the deliberate construction of the physical world. It elevates the task from just construction management to statecraft.
So what is that final command?
It closes with this incredibly powerful call to action. Build where bodies heal and minds rise together. Detail the walls that defend life. Construct knowledge into concrete. This is not architecture alone. This is nation building by design.
A stunning and comprehensive synthesis of strategic intent and practical execution.
And that leads us to our final provocative thought for you, the listener. It's based on that persistent caution we saw across so many of the schemes, the failure that comes from life cycle neglect and a dependency on imported parts. So, if you were the lead engineer and you were tasked with guaranteeing the long-term, low-maintenance success of a modular campus in a highly remote area of West Africa, what single, simple design detail, not a big system, but a small junction or component, what detail would you prioritize to ensure it remains functional and repairable for the next 50 years, relying only on local trades and materials?
So think about that essential vulnerability.
Exactly. Is it the way the roof drains? Is it the standardization of the electrical conduits, the access panel to the plumbing valves? Or something as simple as the specific composition of the door hardware? What simple detail defends the entire system?